Polyprotic. What's that prefix poly mean? Multiple. And so protic is going to be proton. So really what we're talking about is an acid that can release more than one H plus or one hydronium ion is created. So we've got phosphoric acid, we've got phosphorus acid, and carbonic acid, and nitric acid is the outlier here. So we've got triprotic, diprotic, monoprotic. What do we notice about the H's? They're all attached to oxygens, and those oxygens are also attached to something that's attached to a doubly bonded oxygen. So that's the reason the phosphorus acid is, even though it's got the three H's, so it's H3PO3, you would expect all three of those H's to also be acidic, but they're not, because we're missing an oxygen, and so that hydrogen is not attached directly to an oxygen. So that phosphorus hydrogen bond is a lot tighter than the phosphorus oxygen bond. So what do you think about the relative difficulty of pulling off consecutive hydrogens? What do you think happens? So let me back up 1 second. Forget about the nitric for a second. What do you know about these acids that I have up here? Are they weak acids or strong acids? They're all weak acids. Okay, so I've got all these weak acids. So my question is, first question is, when we say weak acid, what is that referring to as far as the ability for the H's to come off? More difficult. It's a small percentage of the H's that actually come off. So like 1 out of 1,000, 1 out of 5,000, something of that nature. Maybe a lot higher, maybe 1 out of 20,000. So I'm going to pluck one off. When I pluck one of these things off, let's use this phosphoric acid. I got an H plus, and I've got H2PO3 minus. Okay, so and again, I will keep writing H plus just because I'm lazy, instead of writing a water molecule plucking off, creating a hydronium ion. So I need you guys to remember that that can't happen. What's really going on is a hydronium ion is being created because a water molecule came over here and yanked off an H. Means the same thing for us. Okay, so now let's think about that second protic H on the phosphoric acid. Since 2 of those H's can come off, tell me about the difficulty of pulling the second one off. Is it the same as the first?
Probably not.
And it is definitely not. Which direction? Easier or harder?
I think it's harder.
So it is harder. And I want you to think about it purely based off of a charge situation. When the first H came off, what was the charge on the phosphorus acid? It's 0. It's a neutral molecule, and I'm trying to pull a positive charge off of it, leaving behind a negative charge. Great. Now I've got what substance? What is the name of this thing? It's a polyatomic ion from that list. Dihydrogen phosphite, and it has a -1 charge. And now I'm going to try to pull an H off of it. Effectively, when I'm pulling an H off, what am I doing to the charges? What's happening there?
Negative.
I'm going to try to make something that's negative lose something that's positive. So is it going to want to do that? It's already negative. I'm trying to pull another plus off of it, making it -2. So it does not want to do that. So it's much more difficult to pull the second H off for all of them. So much so that in the H2SO4, that guy is a strong acid. Sulfuric acid is a strong acid. But once I pull the first H off, that's hydrogen sulfate. And that thing is not a strong acid because it's difficult to pull the second H off because I've already got something that's negative. I'm trying to pull something that's positive off of it already. So it's holding on more tightly because of its charge. All right. Okay, so for this first one, we'll start off with 0.1 molar. We okay with that? That's its concentration. The brackets mean molarity, so I don't have to put the unit in. Okay, so what's the other way to write 0.1? 10 to the negative 1? Okay with that? So the pH for that is 1. We're good? So I take the log and then I take away the negative sign and I end up with 1. So what's the pOH? 13. So then what's this concentration here? 10 to the negative 13.
That is known as accepted.
So what's the first thing you're gonna do for the next one? Super obvious. So we'll put in 1.530 here. Okay. Do you have anything else you can just immediately do without doing any math?
Oh, well, I guess that's not. Oh, H.
You can just write 10 to the negative 1.53. It's not something a lot of people are going to want to see, but it's totally fine. That is a mathematical number that you can write in there. So then now you do a tiny bit of math, which is what?
T minus 1.5. 12.4.
Because again, these things always have to, that and that always have to equal 14. And then you can put 10 to the negative 12.47 for your pOH concentration. So once you realize what's going on, it's super quick and going back and forth. So next one.
OH.
10 to the minus 1 for the OH, right? That's 10 to the minus 13 for the hydrogen ion concentration, 13 for the pH, 1 for the pOH. Yeah, let's do 4. Pretty simple. I want to say basic, but that always gets confusing.
I thought it was gonna be like an equation, but no, it's
Just moving stuff around.
Yeah.
Once you understand what the numbers mean and what they end up with, where they're supposed to go. Okay. All right, so let's talk about some common stuff here. Pure water is 7, and then we've got blood on one side, which is a little above 7, and pee on the other side, which is below 7. I mean, what do you think that range of the urine is based on? 1 absolutely is the amount of dehydration. What else?
Which acid you're drinking.
Yeah, how much for most people in this country, it'd probably be like how much Coke, how much soda are they drinking? Or it could be like, did I order the Carnitas Diablo from the taco shop? I mean, that's definitely going to change the pH for sure.
Acidic.
Coffee is a bit basic, but you usually throw milk in and that ends up dropping the pH a little bit below 7 because of the lactic acid. So, I mean, baking soda is a little above, seawater's got a range that's based off of almost always temperature. Milk of magnesia, that's magnesium hydroxide. So that's that chalky flavored white stuff. Usually they throw some peppermint in. There's the ammonia. You guys should have gotten a pH somewhere between 11 and 12 yesterday when you did that ammonia. And then that last one, that's 1 molar sodium hydroxide, right? And we could make like 10, you can make a little more than 10 molar. So we could get 10 times more concentrated than that. So are their numbers larger than 14? Yes. Are their numbers smaller than 1 for pH? Yes. Are there negative pH numbers? Yes. And we'll show all that stuff, but most people think it goes between 1 and 14. But remember what those numbers are the concentrations of the things that you're looking at. So if the concentrations are very high, then you can be outside the 1 to 14 ratio. Tomatoes, pretty acidic. That goes with ketchup and as well. Oranges are even more acidic. Obviously, if you try to eat an orange like that, you bit your tongue or something like that, it hurts. The cola drinks, we did talk about that. If you put jewelry in there or a tarnished coin in there, that it becomes clean. I mean, you can see it's not even 10 times less concentrated than stomach acid. What do you think would happen if you were to swallow a tarnished penny? It would come out the other side very clean. And so 1 molar hydrochloric acid, you guys have probably spilt that on yourself, and it's not a big deal. So the stomach acid is more than 10 times less concentrated than that. But I mean, it doesn't feel like the 1 molar hydrochloric acid isn't painful to you because the skin on the outside of your skin, all those cells are dead on the exterior. Where if you yak, all of those cells are alive and they're very innervated and they've got lots of nerves, so they understand that they're being hit with an acid concentration when they're supposed to have a pH of 7. Okay. So I know sometimes I tell you things and at the time it's like the best thing for you to hear, but it's not always true. And the last time at the end of the quarter, I told you that things that were insoluble aren't really insoluble. They're really just, they dissolve to an incredibly small KSP value. So the same thing is with the acids and bases. They're soluble. They go in the water, they dissolve. For our uses, the answer to that is yes. But in actuality, they have K values to them. They don't completely disassociate. When HCl goes into water, some of the H's and Cl's do stay stuck together enough to make it matter, not in any way. For all practical purposes, they come separated apart. But hydroiodic acid has the K of 10 to the 11th. So what does a K value with a number like 100 billion mean? Tell me about the ratio of hydroiodic acid in the denominator to H pluses and I minuses in the numerator. Big product, huge numerator, really small denominator. Okay. And you can see that, I mean, nitric doesn't even have, it's just 20. It's a 21 ratio. So for every 20 nitric acids that have separated, one of them still stuck together. So it's not as strong as you might think, although nitric is scary. I wouldn't let nitric touch me. Hydrochloric is way up on that list, right? I mean, it's 10 billion times more strong, but nitric will do more damage to you. Sulfuric will do way more damage to you, even though their K values don't seem to be making them as strong, but they're more dangerous to biological tissues. And the strong bases are between 100 and 1,000 for their K. So again, they separate, but you will still have some of those things floating around stuck together because the hydroxides just do not want to let go. All right, so then we've got some bases here. Do you guys, besides the ammonia, do you know any of these other names up here? Hydrazine is used, was used on our ship to make sure all the water systems stayed basic. Sometimes it might be used in a pool situation or a hot tub situation, but it's probably more expensive than the other options.
What is glycine or glycine?
We just talked about glycine, right? Glycine was that amino acid that I put up for the homework. Methylamine. Have you heard of that? Methylamine was in the news about 10 years ago. Does anybody know? And it was sensational. Anybody know what it was? Owners of Chinese companies are under an enormous amount of stress from the Chinese government to produce money. So the owners of several baby formula companies fudged, faked, spoofed is good, spoofed the protein content test. The protein content tests for amines of amino acids. So when you make formula, you have the proteins, but then you chop the proteins up into smaller pieces using an enzyme to create amines. And then you do a test for amines, and that will tell you what the protein concentration is. So it needs to be a certain number, can't be too high, can't be too low. These guys directed their workers to take the milk and break it down into smaller and smaller segments into the formula. So there would be noticed that this didn't have enough protein in it. So what they did is they took this super cheap chemical called methylamine and threw that in, and it spoofed the test. It made it look like there were lots of amines in there, the correct number of amines in there. So these formulas had the correct number, correct amount of protein. When in actuality, methylamine to an infant can be toxic. So if all the infant is drinking is formula laced with methylamine, they will die. So I don't know if it was in the hundreds, but definitely in the dozens, Chinese babies died. So obviously, as a parent, you find out that formula is killing your kid and you can't breastfeed. There aren't a lot of options. So people that had money, at least, were sending relatives to the United States to buy multiple cases of Similac and then fly back to China. It was very ugly. And at that time when this happened, Hong Kong was still, I mean, it was technically Chinese because that happened in 2000. And this was sometime in the like 2008 or something of that nature. Hong Kong hadn't been fully transferred over into the Chinese control or the communist control. So there were still a lot of companies that were worthwhile to the Chinese government to have functioning. And so you could get the Similac through Hong Kong. There were still a lot of American products there. And the market on it was like $500 for a container of, one container of Similac kind of stuff. When at the grocery store, it's like $12 here. So yeah. And just like with the lead-based paint toys that happened, several of those guys committed suicide through various means and had weird car accidents and stuff like that. Okay. Amine. We know this is an amine because it's an amino acid. Amine, nitrogen. Aniline has a nitrogen in it. You see all of these things have nitrogens in them, right? So all the weak acids that we're going to be looking at are going to have nitrogen in them because that nitrogen has that lone pair of electrons to donate to make a bond, as Lewis would say. So they all come from nitrogen-bearing compounds. There are a heck of a lot less weak bases and bases in general than there are acids. This is a super short list, even though it looks really long. It's a full page, but there's zillions of different acids out there. And we've got Kas and pKas for them. So the Ka can be kind of an unwieldy number to write. And so if you take the pK of it, it's the same thing as pH. So chemists were like, yeah, well, let's just use that pK thing and then just make everything smaller for us. So we don't have to write longer numbers. We don't have to write times 10 to that. So here we have acetic acid and its Ka value. You can look at these guys, they're numbers with negatives to the exponents. So we know that these are all weak acids, even though chromic is close to not being a weak acid. And so each one of these things, the pKa for it is going to be 5, but I've added a little bit more acid to it, so it's going to be a little bit less than that. You understand that? So you could just look at the scientific notation number. And then if there's a number here other than one, then it's just whatever this is and a little bit smaller than that. So here's a 10, there's some stuff there, so it's a little smaller than 10. Here's a 13, there's some stuff here, it's a little bit smaller than 13. So that's a quick way to do the math in your head to see what's going on with that. How come there's two things up here for ascorbic acid, which is vitamin C?
Yeah.
It's diprotic. Two H's can come off. So vitamin C has two acidic H's. One of the reasons that it's super sour. So when you, if you were to brave yourself like a Sour Patch Kid or something like that, do you know what the white powder on the exterior is? I mean, you know, it's super sour. So, and it also obviously has to be edible. It's a combination of citric acid powder and ascorbic acid powder. So if you were going someplace where there weren't any citrus and you didn't think you were going to get any citrus and you're worried about scurvy and you're like, well, I don't know if I can keep oranges and limes, you literally could take like a case of Sour Patch gummy worms or something like that, and you'd be totally fine. So like zombies show up, run to Freddy's and grab a bunch of Sour Patch Kids. Keep yourself from getting scurvy. The zombies can probably smell blood, so don't want that. So you can see boric acid's got 3 different Kas for it because it's triprotic. And you can see that the first one's really hard to get off. And then the second one's 1,000 times harder. And then it doesn't go up that much because there isn't like much more pulling power you can hit. The way you get these things off usually is by using a hydroxide, and the hydroxide's pulling power stops at around 10 to the minus 14th because that's its value. The pH value goes basically to 14, a little past that for the hydroxide, so it can't pull too hard. Do you know any of these other names? Carbonic acid for sure.
Sounds familiar.
That formic, have anybody read Ender's Game? And the aliens in that were called formics. So this comes from ants. That is Latin for insect. And so the reason that formic acid gets called formic acid is because when a fire ant bites you, it's injecting you with formic acid. So that's where that comes from. Obviously, carbonic acid, you know that one. Butanoic acid, that's the acid that's in butter when butter goes rancid. And it's like 2 drops in this room and we'd be gagging. Somebody dropped a bottle when I was in grad school, and the 3rd floor of building 1 was not inhabitable for that summer. Had those like giant fans in the windows blowing it out for weeks. Cyanic acid, that is a poison. Hydrofluoric acid, we've talked about a couple of times. You know, lactic obviously is in milk. Oxalic, that comes cows. Phosphoric, sulfuric, and then uric acid, obviously from urine. All right, so you can look up Ka values, and they basically letting you know the ratio of dissociation of the H from whatever that acid is. And so these all have to be weak acids because the dissociation isn't 100%. All right, so I want to talk about a pH change from an ionic compound. So when I say an ionic compound, I'm saying a salt. So can a salt change pH? And the answer to that is yes. But the caveat is it depends on the salt. So this salt, that's a big no-no. No pH change. So the reason is because the conjugates, all right? So if this disassociates and turns into sodium ion and chloride ion, if I have a water molecule here and a water molecule here, will this chlorine pull an H off of here to make HCl and OH minus? Is that going to happen? Let's say it did happen. What would immediately happen? Did you say trump card? It would fall apart, right? I mean, what is this? That's a strong acid. So if it was in water, it would immediately dissociate itself. So the reason that this will not form, that this can't pull the H off of there, is because the product is something that's fully soluble in water. So it will not stay stuck together. It is a strong acid. So then can the sodium turn into this, leaving behind an H plus? No. We know that the sodium hydroxide is a strong base. Okay, so is this going to happen? It's not, because that's a strong base, right? So the moment, if it did happen, the moment it does happen, the NAs and the OHs are going to separate anyway, so it's not going to happen. So this can't change pH because the conjugate base of sodium is sodium hydroxide, and that's a strong base. And the conjugate acid of chloride is hydrochloric acid, and that's a strong acid. And that sounds like they're both strong, so it's going to change it. And the exact opposite is true. They're both strong, which means they can never form in water. So what I'm looking for is the anion has the ability to form a weak acid, or the cation has the ability to form a weak base. Okay, so what I need is some substance that will turn into a weak acid or base, and then I can get the pH to change. So the classic one is sodium fluoride. This is the active ingredient in toothpaste. This is when they say the toothpaste is fluoride, it's sodium fluoride that the toothpaste is. So let's say I've got solid sodium fluoride. It touches water. What's going to happen? We okay with that? It's a sodium ion, so it's fully soluble. So I get the Na and the F to disassociate. Well, we just talked about the sodium, right? Can the sodium change the pH? No, because the conjugate base is sodium hydroxide, and that's a strong base, so it can't do anything. But the fluorine, that's what the fluorine does to the water molecule. Now, why does the fluorine do this to the water molecule? What kind of acid is HF? It's a weak acid. Okay, so when we think about a weak acid, we think about the fact that the HF doesn't want to separate, all right? But what if it's already been separated? In this case, it's been separated. So what is it going to try to do? Reform. So that's really, when we're talking about using weak acids or bases, conjugates, it's because they're trying to reform themselves. And when they do, they're getting their H's or their OHs from water molecules, leaving behind an acid or a base. So in this case, I put sodium fluoride in water, and the base, it becomes basic, and the pH goes up. I don't think that's the case with toothpaste. I'm pretty sure they cut it with an acid to make sure that you don't get, I mean, nobody would want to put toothpaste in their mouth if it was bitter. So I'm pretty sure they crushed it with another acid.
Would we call the water here an acid technically?
The water is absolutely the acid, and the base is the fluorine. And so Arrhenius doesn't work here, but Bronsted-Lowry do, because the water donates an H, donates a proton, and the fluoride accepts the proton. The other way to think about it is Lewis, that always works. Fluoride's got all these lone pairs of electrons around it, so it's donating those electrons, so it's a base, and then the water is accepting those with the H, and so that makes the water the acid. Does that make sense? So I add a salt to water, and I can get the pH to, in this case, go up, and that's what we're looking at with ionic substances having the ability to change the pH of water. Questions about that? Let's do the opposite. This touches water, and what does it do? This is ammonium chloride.
If they go ahead for it and seal. Is that how it?
Ammonium compounds are soluble, highly soluble, and chlorides are soluble. So it separates. So is the chloride going to do anything? So when you ask yourself that question, you have an ion that's negatively charged. Put an H on it to cancel out the negative charge. So now I go from Cl negative to HCl. What kind of acid is that? Strong. So that can't change pH because it won't form because it stays disassociated. So this one up here, we had sodium. Since this is a cation, add an OH to it and then say what kind of base it is. And so it's sodium hydroxide. That's a strong base that can't form because strong means they won't come together. So now I've got NH4 plus. I could put an OH on that. And that is not a strong base. So let's come down here. That one is going to be able to affect pH. So what's going to happen here?
Accepting an oxygen.
No.
Okay, it's actually the acid. So now you said yesterday or Monday.
Yeah, so let's look at this for a second. Of these two things, which one is the acid? Water could be either or, right? So let's not look at the water. Let's look at the ammonia. Can the ammonia grab another H? No, it can't. It can only make 4 bonds. So what the ammonia can do is turn, ammonium ion can do is turn back into ammonia. So it can drop an H. So that is why it is the acid. And so the water molecule is providing the electrons, as Lewis would say. And so I put ammonium chloride in water, and what happened to the pH of the water? Lower. I added more acid to the water. Is that good? So acids can obviously change pH, bases can change pH, and now we know salts can change pH if one of the two ions has a weak conjugate, a weak acid or a weak base. Okay. That's all I got for today.